Hi, welcome back. I am going to continue from where we last left off and discuss what goes ahead of what we talked about last time, namely the kinetic gas theory and average molecular velocities. If you remember, we calculated these for lysozyme. We then discussed that if molecules can't actually move like bullets in a ballistic fashion, then they're more likely to be performing some kind of collisions, that there's no independence of the individual molecule walking, and that it might describe something called a drunkard's walk or a random walk. And we discussed the statistics of the random walk because some very nice properties come without assuming anything physical. The point of raising drunkards walking, besides the entertainment value, is that the statistical properties are independent of the underlying phenomenon, and this is a beautiful process, right? Because you can see that we didn't have to say anything about whether it's an old drunkard, a male drunkard, a female drunkard, a non-binary drunkard, child drunkard, grandpa drunkard. It doesn't matter whether it's a molecule or polymer. We then ended with saying that if the step size average is not 1, but in fact Kuhn's length A, then the mean squared end-to-end distance position at the end becomes equal to NA square, because it was, in fact, we ignored that 1 in the simple arithmetic. And I ended with a question about rubber elasticity, which is due for Thursday. I'm going to come back to that in a bit. So for today, I want to talk to you about random walk polymers and probabilistic arrangements, average distributions of polymers, persistence length, and relating Kuhn and persistence length to each other, ending with radius of gyration, which is again a part of your assignment for next week, and I hope you are eagerly looking at it. At least you've had a look at it. If you have questions, Thursday is the right time for you to discuss it with me. If there are any clarifications, obviously I can't give you the answers, but I can help you get to them. Okay, so let's go ahead. So I mentioned to you that rubber elasticity has an unusual property, and this is sort of seen in this diagrammatic view, that it consists of many fibrils or polymers, in other words, which can be either stretched to extend them, yeah, or when they're released, they retract and they become relaxed again, which in the case of polymers is a more compact form. So we are trying to say that as the stretch is released, the force stretching it is released, the retraction actually results in an entropy increase. Yeah? And that is related to the idea that when you stretch, we expect the polymer to warm up, and when you release it, retract it, we expect it to cool down. For Thursday, I'd like all of you to please bring a rubber band so that we can test this out. Okay. The idea is that there's something happening to the temperature of the material when we stretch it and when we relax it, and that is exactly the part of my question to you for a written reply as an assignment. Indeed, metal springs are considered to be enthalpic machines, and rubber bands are considered to be entropic machines or entropic springs. And this hopefully gives you the hint to the answer, but without hopefully revealing the whole answer. So indeed, what is the special property that makes random walk polymers so unusual? I said this last time also, that if we consider a one-dimensional or even a three-dimensional discretized polymer, meaning to say we consider little rod segments which, let's say in one dimension for simplicity, they flip one way, choose another segment, flip another way, and so on and so forth independently, flipping a coin effectively, going either left or right, a random walk. And in 3D you have more degrees of freedom. These rigid segments then we call Kuhn segments, which are inflexible in the sense that they are of a fixed length and they do not bend or turn, but they are connected by flexible hinges, and this is why this model is also called freely jointed chain. Yeah, it's like your necklace. I mean, some of you have these beautiful necklaces with segments. These segments may be little beads or cylinders, and the cylinders have little complete flexible joints. Here, for simplicity, we assume only 90-degree swaps in 3D. Okay. So if we consider now, coming back to the one-dimensional case, a chain, a freely jointed chain of 3 segments, then we have a whole bunch of possibilities that we can arrange this polymer in. So we can either have them as taking 3 steps to the right, 3 steps to the left, yeah? 1 step to the right, 1 step to the left, 1 step to the right. So 2 steps to the right, 1 steps to the left. But in that sequence, then we have 1 step to the left, 2 steps to the right. So still 2 steps to the right, but slightly different arrangement, as you see. 2 steps to the right and 1 step to the left, and so on and so forth. So if we are to find out the multiplicity that arises, the possible conformations that arise out of a certain number of steps to the right, then we have a very easy recourse to going back to our binomial coefficient to count the number of ways we can arrange it. So let's ask the first question. When we take, in the top case here, when we take 3 steps to the right, how many ways are there of arranging it? When we take 3 steps to the left, how many ways are there of arranging it? When we take 1 step to the right, 1 step to the left, 1 step to the right, how many ways are there of arranging it, and so on and so forth. And as you will see, the answer to that question comes as 1 for all right steps or all left steps, and the multiplicity increases when they are not just, all 3 steps are not right or left necessarily. And this is again intuitive, but I'd like you to ponder on it. Okay. So the polymer end-to-end probability, that is to say, what is the density distribution after all these steps are taken? I mean, what we talked about initially was just the discretized version. We took steps left, took steps right, we kind of did the calculation. But what if you calculate the average? If you do this 100,000 times, there are hundreds of segments, there are hundreds of polymers, what will the probability of overall departure from the origin be? In that case, we come back to the binomial coefficient times 1 by 2 to the power n, and that is solved or resolved by arriving at an approximate Gaussian distribution of the probability of end-to-end distance. I want you to stare at this expression down below, where P of end-to-end distance R for n steps, meaning n segments, so we've gone from drunkards to rigid rods, Kuhn segments, is equal to 1 upon the segment length A into the under root term 2 pi n, n being the number of steps or segments, and all this product of exponential in negative half r square end-to-end distance upon na square. Yeah, you can see this here. Now, this is indeed a Gaussian, and indeed if you plot this for a 100 segment polymer, you exactly get a Gaussian, and you can in fact compare it to the standard Gaussian distribution, which you hopefully done in biostatistics or high school or I don't know where. It in fact tells you that the term A that we have been referring to as segment length can be easily mapped to sigma, yeah? And n in that case disappears in the Gaussian distribution. The numerator with the exponential term has the equivalence of sigma is equal to a root n, and that's how that n disappeared, by the way, right? And mu or x minus mu is r. It's the mean displaced distance from initial position, assuming x is 0, all of that squared. This, by the way, the Gaussian distribution comes from the central limit theorem, which I suspect you have had to study at some point. And because I'm not going to elaborate on it, but I'm going to ask you when we meet on Thursday, what is the central limit theorem? So in 3 dimensions, so this was 1 dimension obviously, this equation becomes a little more elaborate. It is 3 by 2, 2 pi na square. So because of that na square, we have to take 1 by 2 in the power and 3 to the power 3 because 3 dimensions, and e to the power minus 3 by 2 r upon a root n whole square. The interesting part of this is that the highest probability, as you also saw in this graphic for a one-dimensional system, the highest probability, highest density of finding end-to-end distances is 0. Yeah? So, and this is true of a random walk also, which is another way of saying that the drunkard is not going to get very far. Yeah, the most likely position the drunkard will be at is the lamppost, or the fibers, the polymers in a rubber are most likely to be compact. This is a very strange way of looking at things, because in our normal spring mass system, in the spring, the reason why we say they are going to reach a certain position is because the spring, the atomic springs have a certain resting length, and that is the energy that we described using Lennard-Jones potential of interatomic interactions. Here, this is purely statistical. Yeah? And this is the beauty of it. And this is why I had spent so much time talking also about the osmotic engine. But let's go ahead, not backwards. So we now come to a term which we will refer to as persistence length. And we've talked about this earlier. I'm going to do a slightly more detailed effort at trying to get at it. So persistence length by definition is supposed to be the length over which a polymer is essentially straight. And it considers local rigidity, the tangents to the polymer T of S1, T of S2 at distances S1 and S2 in a freely jointed chain. Yeah. So let's see what we can do about it. So we just talked about random walk polymers, statistics and average probability distributions, and we want to continue with persistence length. And in order to do that, we want to maybe discuss very briefly the so-called Ergodic Theorem, which tells us that nearly every microstate approaches the arbitrarily close to the all of the true states of the corresponding ensemble in the course of time. And a system that follows this, therefore, is then following the Ergodic theorem. And I encourage you to look at your physical chemistry and statistical mechanics textbooks to refer to it again. And the second thing we also rely on for kind of getting at the persistence length is the Boltzmann's postulate, the time average of Boltzmann's postulate, that the time average of an isolated system is the average over all states in the microcanonical ensemble. And as I had sort of mentioned in the slide, the persistence length of a system, of a polymer in this case, is based on taking tangents to the polymer along its length with increasing distance between the tangents, or the points at which the tangents are taken. So if we call this tangent t at 0, then we can call this tangent at t at s, where s is nothing but the contour length between the two positions, and this can be s1, s2, and so on and so forth, right? Where then the contour length becomes s2, which is of course the whole length from here to here, whereas this one is just s1. So we define t as the tangent and s as the contour distance or contour length, separating 2 points on an arc. This arc is nothing but the one that defines the polymer. Yeah? In such a case, the question we ask ourselves is, what is the nature of the tangent-tangent correlation and what is its functional form? Nature of the correlation between the tangents. In other words, functional form. Now, some of you already know this perhaps, and either way, we're going to guess. And the guess we're going to make is that we're going to say, well, we took the tangent at some initial position tau plus s, and we tried to find its correlation, its product with t at tau, okay, where tau is just some point on the contour. Right? Then indeed the tangent is a unit vector, right? And tau plus s is the length of the curve from tau, right? So that we have a non-zero start point. In such a case, if we want to infer what this g of s becomes, then we have possibly two cases that we want to consider. One case is that s is equal to 0, and the other that s is equal to s is much greater than the region over which the polymer is straight. In other words, it is very winding. So if we are considering a very windy polymer, then if this was tau and s was very long, then we would probably be referring to something like this. Yeah, much greater than the region over which the polymer is straight. And when s is 0, then it's essentially like taking the tangent at the same position. I've drawn it in slightly different directions just for clarity. This would imply that g of s, which is nothing but the dot product of two vectors averaged, right? I sometimes have been skipping the vector signs, but bear in mind that was not intentional. So t cap or t bar of tau dot product with t cap of s plus tau or tau plus s averaged for angle of 0 is nothing but the product of the two magnitudes of the vectors times cos theta. Cos theta of 0 is 1, therefore it is nothing but 1. In the case that the two angles are not correlated, they are not 0, then they can be all kinds of angles, right? So essentially these two vectors at tau can be tau and tau plus s can take any various angles, right? And I'm assuming 180-degree mirroring. That would mean that on an average I have about pi by 2, and then that makes my cos theta cos pi by 2, which is nothing but 0 multiplied by everything 0. So this is the nature of this g of s, qualitative nature. So the question becomes, what function satisfies this condition that when s is 0, the value is 1, and s is much larger and it decays, right? It is 0. And the function that fulfills these requirements is surprising, or not very surprisingly, nothing but the exponential, where we say that the coefficient of the exponent the decay, exponential decay, is in fact the persistence length. It's like saying that the correlation, like we said, goes from 1 to 0 for increasing s such that it is a continuous function with a characteristic decay length of persistence length. Okay? And that's in a way our idea of how we can intuitively understand the meaning of the exponential. There are more formal derivations and I am not going to do those. The second as maybe line of evidence is that when there are two adjacent segments, then and they are buffeted by thermal effects, that is diffusion, then the correlation function g of S1 plus g of S2 should effectively, due to the fact that they are independent of each other, be the sum of S1 and S2. And this property is also satisfied by the exponential, where exponential of x plus y can be written indeed as exponential of x plus exponential of y. Yeah, sum of exponentials. So all this being as it is, we can indeed now write the tangent-tangent correlation, the dot product of the two tangents, t cap of S1 times t cap of S2 averaged as e to the power minus magnitude of the distance between these two segments divided by Cp, some constant, which indeed is the characteristic length. So we can, to summarize, say that when S is equal to L, then indeed g of S is 0, and when S is equal to 0, then g of S is equal to 1. In other words, when the segments that we are looking at, the contours, are the identical contour, then that correlation term is 1. Just to give you a sense of the order of magnitude, and I may have discussed this in the bending rigidity measurements, but let us take a biopolymer that we all are very familiar with, DNA. It always catches everyone's imagination, and we take it from a virus, the lambda phage. Then the number of bases of the lambda phage genome is 48,490 base pairs. The contour length is n, this number of base pairs, into 0.34 nanometers per base pair, which turns out to be 16.4866 micrometers. Yeah? By experiments, it has been found that the persistence length of DNA is equal to 50 nanometers, which in base pair terms is 147.05 base pairs, which we can approximate to 150 base pairs. In other words, 150 base pairs of DNA are effectively are persistent. Yeah? And this is where we want to perhaps relate the two terms that we have now brought up. One is indeed what I have been mentioning right now, which is persistence length, and the other is the one we started with, that is Kuhn's length. So the question is persistence and Kuhn length, how are they related? Yeah. So if we assume an actual rod, yeah, so cylinder may be bent at times, but then the end-to-end distance of a rod can just simply be given as the integral over the whole length of every segment of that length times the tangent to that system, right? So when ds is small, so this assumption is that ds are small segments, right? And the tangents are at every successive segment length of s. Then the average squared end-to-end distance for such a rod can also be written as the integral over length L ds1 for some segment s1 times the unit vector of the tangent at that position integrated over the same thing for the second segment. And this becomes relevant when our structure is not anymore a straight rod, because then this just simply holds true and there's nothing more to it, but when there is a random walk polymer. So for a freely jointed chain or random walk polymer, T cap of S1 times T cap of S2, we said by definition is equal to e to the power minus magnitude of the difference between the two segments by Cp in negative exponential terms. So we want to try to do something with this expression above, and for that we split the integral into two conditions, one where S1 is greater than S2, and for obvious reasons where the opposite is true, S1 is less than S2. Since we assume that these have equal contributions, we can just simply rewrite the R e to e squared averaged distance as 2 times a common integral 0 to L ds1 S1 minus S2, the difference. In the limit that the contour length is much greater than Cp, which is reasonable, we can subtract delta S from the upper and lower limits over here, yeah, and end up with something that looks like this, which is R e to e squared is approximately equal to 2 remains to 0 to L ds 0 to infinity d delta S e to the power minus delta s upon, this should be delta s upon Cp. But because, and this is all because L minus delta S is approximately equal to L, and true when L is much greater than persistence length, leaving us with a simplification of end-to-end distance squared average is equal to 2 L Cp. Yeah? But we know that L is proportional to N. That is, from random walk statistics, L is equal to, and L is proportional to N, and R square, the end-to-end distance, is proportional to N, because, as I was trying to write, not L but R square is equal to NA square, right? Therefore, R square average end to end is equal to LA. This is obvious, this is the contour length, is equal to 2L Cp from here. Therefore, A is equal to 2 Cp. So this answers our question, what is the relationship between Kuhn's length and persistence length? So we wanted to define one more term. So that was the radius of gyration. Rg, and we know that the Rg, and this is also in the tutorial, in the assignment, the squared value of Rg is nothing but the average of the over all segments, all positions, or if you are talking about atoms, then atoms, Ri minus Rcm squared. So what is Rcm? It is nothing but the position vector corresponding to the center of mass. By definition, R of Cm, the vector Rcm, is equal to 1 upon n summation I is equal to 1 over up to n of all positions of all elements of the system. In other words, it is nothing but the average vector. So you're finding the deviation, squared deviation of the average vector from every atom and averaging it, right? It turns out that you can write this, the average radius of gyration, or the root mean square radius of gyration for a random walk polymer, as L Cp upon 3. And I leave this for you to try to prove if you want to test it. Suffice to say, we are going to use this number as a result. In order to find some order of magnitude estimates of radius of gyration, we can indeed use the fact that experimentally measured values of Cp for DNA are 147 base pairs, which is 150 base pairs approximately, which is approximately 50 nanometers. And for proteins, this is approximately a nanometer. All right. So we return to a concept from persistence length and radius of gyration to a Flory temperature, before which I have now basically taken from the textbook a plot of the solution to the radius of gyration arithmetic by substituting L, the length of the polymer, as 0.34 nanometers times base pairs, therefore 1 by 3 root n base pairs times Cp for DNA alone. And here you're looking at a log-log plot of the radius of gyration on the y-axis and base pair lengths on the x-axis. And on this log-log plot, these data sets seem to fall on a straight line, with lambda phage at the lower limit and human chromosome 1 at the upper limit. There is an issue with the fact that the end-to-end distance is related in real polymers to a scaling factor referred to as the Flory temperature. Because real polymer chains are known to interact with the solvent, and the strength of interaction determines the attraction and repulsion. So intermediate temperatures where the chains are in an ideal conformation, where attractive and repulsive monomer interactions cancel out, is then referred to as Flory temperature. Paul Flory was again a Nobel laureate for his fundamental achievements in the physical chemistry of macromolecules, in some senses a pioneer of polymers. So the flexibility of ideal chains can be considered with very simple non-biological chains such as polyethylene, which have canonical 68 degrees between each chain position, and the torsion angles determine flexibility. Number of bonds and bond lengths are then geometrically determined, and these can be then used to find the so-called Rmax value, which is geometrically n times the length of each rigid segment cos theta by 2, which is the angle between every segment. And then the ideal bond vector relations gives us back, for a freely jointed chain which has no correlation between bond vectors, distant ones, of R square n L square, which is recovering our random walk of freely jointed chain statistics. But for so-called real chain bond vectors, there is a scaling factor of Cn, which is Flory's characteristic ratio. Indeed, an infinite chain has n infinitely long, obviously, and then the mean square end-to-end distance of that becomes R square is C infinity plus NL times NL square. Indeed, the bond and Kuhn lengths are also then slightly modified by this Flory's characteristic ratio. I said that you can get at a order of magnitude of persistence length with DNA, but you can also get at a radius of gyration for DNA. And remember, we said that random walk polymers or freely jointed chains always want to come to the center. In other words, they are highly dense at the center. The probability of their density is highest at the center, and it decays in a Gaussian fashion in 1D, 2D, and 3D. So it is interesting to note that when in the image down below in an electron micrograph, the cell was lysed and the DNA was stained in electron micrograph, then with a persistence length of 50 nanometers, the radius of gyration comes to 5 microns. And remember, we always talk about the scale of an E. coli cell. This is about 2 microns, is the longest size of a non-dividing cell. In a dividing cell, you can claim 4 microns. In effect, circularly, the DNA that comes out of a burst E. coli cell is much larger than the cell itself. What this should tell you that not just in eukaryotes, but even in prokaryotes, somehow the DNA is packed and organized so that it can nicely fit in and perform its functions despite being packed so tightly. And this is now a simple list of sequence lengths and of human DNA, just to remind you that these vary quite a lot, and individual chromosomes, individual chromosomes of the human genome at least have 3, 6, 10 to the power 9 base pairs order of magnitude lengths, 0.1, 0.2 or even higher in some cases. And this is quite fascinating because if I told you that the genome length of bacteria has a radius of gyration of 5 microns as a free polymer, yeah, and you should be able to see this on the scale bar also, by the way. This is not just speculation or theory. This is coming also out of experiments. In other words, reconciliation of experiments and theory. So in the same way, the human genome is going to be much longer. You are free to calculate this, and I'm going to ask you this question on Thursday. What is the average Rg of the human genome? You will have to make some assumptions, but I'd like you to do this arithmetic anyway. As it turns out, DNA in eukaryotes and especially in humans, which has been very well studied, is tightly packed. And you are tightly packing it, but when you segregate it, it kind of decondenses. Or rather, it condenses even further. And it has to be correctly segregated. And the cycles of compaction, decompaction have to do it right? I mean, you need to get it in the correct place because as you see in the image over here, the blue marker indicates what happens when you don't correctly segregate it and you end up with more than one copy of a chromosome. This indeed is an unfortunate case of a disease called Down's syndrome, right? So chromatin organization is indeed seen to involve the packing of, this Chinese noodle style appearance of DNA into increasingly more complex structures. So when we return, we are going to discuss what these complex structures are, what are their dimensions, what consequences do they have for our understanding of human genome and its organization, and how far are we with a complete understanding of packing with a connection back to polymer theory, right? So thank you very much for listening, and I'm going to stop.